Hi, this is a presentation of my paper Recipes in Economic Growth, a combinatorial march down an exponential tail based on a presentation I did last week at the NBER Summer Institute. So this paper builds on two strands of the growth literature. The first are these great papers by Weitzman and Romer that suggested combinatorics are important for growth. So Romer used to go around in the early 90s and talk about all the number of combinations you can make from existing ideas or existing ingredients. So think about the number of things you can make from a child's chemistry set. Combining everything, you get more than the number of atoms in the universe. Weitzman in 1998, in a beautiful paper, built a model around combinatorics. But interestingly, combinatorics is basically absent from state-of-the-art growth models. So that's kind of the first thing. What happened to combinatorics? The second contribution builds on this paper by Kortum in 1997, which was a precursor to Eaton and Kortum and all the Fréchet distributions that we see in the trade literature and also in the growth literature now. Kortum had a different way of thinking about growth. The notion was you're drawing productivities out of a hat from some distribution, and you only keep the highest productivity you've ever drawn and use that one. You keep the best idea. And so you draw a 3, that's your productivity. You draw a 7, that's your productivity. You draw a 2, you throw away the 2 and you keep the 7. And Kortum's question was, what assumptions do you need to make on that process to get exponential growth in the max, exponential growth in productivity? And it turned out he needed 2 assumptions. He needed the rate at which you're drawing to grow exponentially. So think about population growth and the number of researchers. That's how Kortum in 97 thought about it. But importantly, you also need to be drawing from a Pareto distribution, or at least a distribution that's Pareto in the upper tail. And what's strange about that is we see lots of Pareto distributions in lots of places in economics for the size distribution of cities or firms or income or wealth. But everywhere we see it, starting with this Gebek's 1999 paper, we derive it as an endogenous outcome. We ask, why is the size distribution of firms Pareto? Lutmer worked a lot on that. Why is the income distribution Pareto? Why is the Pareto exponent for the income distribution changing? And in that literature, the Pareto distribution results from economic growth. So, a natural question to ask about this Kortum paper is, do you really need the Pareto assumption? And it's odd because everywhere else we see Pareto, it's a result rather than assumption. So that's kind of the second motivation for the paper. The paper has 2 contributions. One is a simple but useful theorem about extreme values. It's much simpler than other extreme value results. I'll show it to you in a second. And it basically says, it's a way to characterize how the max extreme value grows as a function of the number of draws and the shape of the upper tail for essentially any distribution. So it's a nice, simple, useful result for growth theory. And the second contribution of the paper is to apply it to growth theory. To see the application, I need to define what I mean by combinatorial growth. Okay, so think about the number of recipes you can include in a cookbook if you have n ingredients. So every ingredient can be in or out of a recipe. And so the number of recipes you can make from n ingredients is 2 to the n. Okay, what I mean by combinatorial growth is 2 to the n, where n grows exponentially. And again, I'll think about the exponential growth in ingredients as resulting from population growth and the number of researchers. But 2 to the n, where n grows exponentially, that's combinatorial growth. And obviously, that's much, much faster than exponential growth. Okay, the key result in the growth paper is if you've got combinatorial growth in the number of draws, so you've got this cookbook model of research, then draws from thin-tailed distributions are enough to give you exponential growth in the max. So draws from a normal distribution or an exponential or lots of common distributions, and I'll be precise about the class of distributions that deliver this and what happens if you're not in that class. So the bottom line here is Pareto distributions aren't required. You just need to draw faster from a thinner tail. And it turns out combinatorics is exactly the right way you need to draw from a lot of standard distributions like the normal or exponential. Okay, here's the theorem, a simple extreme value result. Let zk denote the max value from k IID draws from some continuous distribution f. Okay, and since we're focusing on the max, it's useful to define the tail of the distribution, the complement of the CDF, f bar of x, is 1 minus f of x. So f bar of x is what's the probability your next draw is bigger than x, okay? And let f bar of x be strictly decreasing. So this sort of continuous distribution, strictly decreasing, is going to be, sort of technical conditions that are helpful. And the surprising, interesting result here is, okay, zk is a random variable. F bar of zk is just some transformation of the random variable, some new random variable, and multiply that by k. What turns out to be true is k times f bar of zk, this new random variable, has a distribution that's asymptotically just a standard exponential distribution, no matter what f you're drawing from, okay? The f bar undoes the distribution, so you just get a standard exponential. And so the way to think about this is as k increases, the max zk is also rising, but it rises in precisely the right way to stabilize k times f bar of zk. And so you've got some tail of the distribution f bar, and you've got k increasing. Well, the max zk is going to rise exactly so that this new transformation is stationary. Okay. Some really nice intuition for this comes quickly. So we can write our result, just kf bar of zk is a standard exponential random variable plus something that disappears asymptotically, okay? If you think about what this means, it says that f bar of zk, which remember is just what's the probability your next draw is larger than the current max. Well, this theorem just says the probability your next draw is bigger than zk, apart from the noise, is just 1 over k. All right. It just, no matter what distribution you're drawing from, the probability your next draw is bigger than zk looks like 1 over k. And this is kind of a well-known result from the theory of records. Suppose you have k IID draws for temperature. Okay, we're keeping the record temperatures in Palo Alto. All right, and we've got k observations, k days of temperatures to draw from. Well, the unconditional probability that today's a new record high is just 1 over k. It's IID, so any day could be the record. If you've got k days, the probability that today's the record high is just 1 over k. Well, this result is similar, but it's conditional instead of unconditional. We're saying we've seen the max. We know the highest temperature is zk. It's still, apart from noise, the probability that today's a record is kind of 1 over k. All right, so what this says is that f bar of zk falls like 1 over k for any distribution. And so apart from the noise, zk rises like f bar inverse of 1 over k. And that tells you exactly how zk rises as a function of the number of draws k, and for any distribution, kind of f bar here. Okay, so now let's, well, here's the proof. It's a really simple result. I'm not going to spend any time on the proof because I want to keep the video short, but it's almost trivial to prove once you see the right thing. Okay, so now we can see Kortum's key insight in one slide. Okay, so Kortum says we're drawing from a Pareto distribution. So f bar of x is a power function. It's x to the minus beta, right? Power functions play a key role in all growth theory. You'll see that again in a little bit. Okay, substitute into our theorem, k times f bar of zk. Well, it's just k times zk to the minus beta, and solve that for zk, right? You need to, flip it over, and you get zk divided by k to the 1 over beta is our standard exponential random variable raised to the power negative 1 over beta. Interestingly, a standard exponential raised to the power negative 1 over beta is Frechet. So that's where Frechet comes from. For everything I'm talking about today, basically, I don't care about the Frechet part. What I care about is the max zk. If you want something that's stationary, you have to divide it by k to the 1 over beta. And that's what detrends this max ratio. And so what you can see here is exponential growth in the number of draws leads to exponential growth in the max. And the growth rate of the max, again, apart from the noise, is the growth rate of the number of draws divided by beta. It's the growth rate of the number of draws deflated by how thin is the tail of the Pareto distribution, which I like to think of as the rate at which ideas are becoming harder to find. So the growth rate in Kortum, growth rate of number of draws deflated by how hard ideas are to find. Okay. Now, the canonical example in my paper is not going to be the Pareto distribution, but instead is the Weibull distribution. Okay, and the Weibull distribution has a tail CDF, f bar, that's e to the minus x to the beta. Okay, so if beta is 1, this is just an exponential. So the exponential fits right in this class. And we've just generalized it to let the tail have a power function to it. Okay. So again, k times f bar of zk is just our epsilon. Substitute in that f bar of zk is e to the minus zk to the beta, and solve for zk. And now you need to take logs because you've got this exponential. And what you see is that zk, well, notice that zk rises with the log of k to the 1 over beta, and then you've got the noise. If you divide everything by the log of k to the 1 over beta, in fact, you divide the noise by the log of k here as well. And so the convergence now is convergence in probability, not convergence in distribution. All right. So this max zk, what do you have to divide it by to detrend it? The log of k to the 1 over beta power. All right. So for example, if k were to grow exponentially and we had beta equals 1, so suppose we're drawing from an exponential distribution, well, then the max is going to grow linearly. And again, that's a well-known result. That was even in Kortum 97. And that was why Kortum said, look, you can't have, if k is growing exponentially, then draws from an exponential distribution lead to linear growth rather than exponential growth. And so that's why he kind of needed Pareto. But more generally here, if k is growing exponentially, the growth rate is going to fall to 0 for any beta in this Weibull distribution. So you don't get exponential growth. But if you look at this equation again, you realize, hey, what if I made the log of the number of draws grow exponentially? Well, if the log of the number of draws grows exponentially, then we're back in business. Then the max is going to grow exponentially again. And it turns out combinatorial growth is exactly that, right? K is 2 to the n. The log of k is just n log 2, and n is growing exponentially, right? So the growth rate of z withdraws from a Weibull distribution is the growth rate of the log of k. If we've got this combinatorial growth, this cookbook model, then the log of k grows exponentially at rate gn, and the growth rate of the max is just the growth rate of the number of ingredients that are being used in our cookbook, deflated by how thin is the Weibull tail, right? So combinatorial growth withdraws from a Weibull distribution, delivers exponential growth in the max. All right. So you might ask, what happens to, if you draw from other distributions? And so the next result in the paper, well, I'm skipping over the growth model. So you can take this sort of insight and embed it in a growth model like Kortum 97, except you're drawing from a Weibull distribution instead of, a Pareto distribution, and you've got a combinatorial growth model instead of an exponential growth model for the number of draws. But then the next result is look back at that growth model and now let Z be drawn from a general distribution, right? Continuous and unbounded. Let eta of x denote the elasticity of the tail CDF. Okay, so eta of x is d log f bar d log x. That's a negative number, so we take a negative of that to make it positive. So eta of x is the elasticity of the tail CDF. And the nice result here is an if and only if result. If you want exponential growth in the max at a rate gn deflated by some value alpha, you get that if and only if the elasticity of the tail CDF is asymptotically a power function with exponent alpha. Okay, so that's just restating the result. What you see here is that we've got a thinner tail. Thinner tails require faster draws, but they still require power functions. Power functions are absolutely essential in growth models. What's going on here is it's just the elasticity itself is now a power function. Okay, so now, for example, you can see why the Weibull I said is the canonical example from the paper. F bar of x is e to the minus x to the beta. The elasticity of the tail CDF is just directly a power function, not an asymptotically a power function. It's always a power function, x to the beta. Interestingly, think about the normal distribution. The normal distribution is the integral of e to the minus u squared. Well, that looks a lot like the e to the minus x to the beta with beta equals 2. That turns out to be true. The normal distribution has the elasticity of the tail CDF asymptotically equal to a power function x squared. So it's just like the Weibull with beta equals 2 for this purpose. Another bit of intuition, go back to Kortum 97 with the Pareto distribution. With the Pareto distribution, f bar itself was a power function, so the elasticity is just constant. It's just a constant beta, and we saw that exponential growth in the number of draws was enough to deliver exponential growth in the max. Here, with the Weibull distribution, f bar is the exponential of a power function, And so it's exponentially thinner than a Pareto distribution. And we have to march down the tail exponentially faster. We've got exponentially thinner tails. You have to march down it exponentially faster. And that's what combinatorial growth is. Notice there's nothing special about the number 2 here. That could have been a 3 or a 37 or an e. It could be e to the nt. That's what I mean by you march down the tail exponentially faster. Okay, so for what distribution do combinatorial draws generate exponential growth? You can apply that theorem: normal, exponential, Weibull, Gumbel, gamma, logistic, generalized Weibull, let it be a power function times the exponential, or the exponential of a polynomial. All of these are going to work. Equally interesting is, when does it not work? And in particular, something you thought might have worked is the log normal distribution. But if you think about it for a second, you realize that can't be the case, right? Log transformations and growth models break things. If it works for the normal distribution, then the log normal distribution means the log of x is normal. That means percentage increments in productivity are normal, but that's going to make the tail too thick. Log transformations break things in growth models. Another way to see that, suppose the log of x is drawn from an exponential distribution. Well, that's going to break again. It works for the exponential, but the log of x being exponential is just a Pareto distribution, and that tail would be too thick. Combinatorial growth with draws from our Pareto distribution would generate faster than exponential growth. Another thing you can do, you can use that first result, the extreme value result, to say, how does the max behave for any distribution? Okay, so for the exponential in the Gumbel, it rises with the log of k. For the Weibull, it rises with the log of k to the 1 over beta power. For the normal, it rises with the square root of the log of k. For the log normal, it rises with the exponential of the square root of the log of k. For the Gomper, it's a distribution that's used to model life expectancy. And that tail is actually very thin. It rises with the log of k. So with combinatorial growth in the number of draws, you would only get arithmetic or linear growth in the max there. Then interestingly, you can ask, think about the Romer model. The Romer model is you get 10 draws per year. Can 10 draws per year generate exponential growth in the max? Kortum didn't think so, because he was using standard extreme value theory. But it turns out, using my first result, that theorem 1, you could do it. You just need the number of draws. You need the draws to be from a log Pareto distribution. The log of productivity is drawn from Pareto, and the Pareto parameter has to exactly equal 1, and then you would get something very much like the Romer model. Now, that doesn't work in practice. The tail's too thick, the variance explodes. It's not a good model, but it's interesting that you can back it out. 10 draws from a stationary distribution can generate exponential growth in the max if the tail is thick enough. And log Pareto with the mean of the Pareto distribution not even existing is the right thickness there. Okay, last thing I want to do really quickly is talk about evidence. So when I got to this point in the project, even I was wondering, is all of this just mathematical tricks and everything's observationally equivalent, or is there really something economically different? And it turns out there's definitely something economically different. And you can see that by thinking about patents. So Kortum 97 was designed to match a key fact, and I put the fact in quotes, I'll show you the data in a second, that the flow of new patents that exceed the previous state of the art, was stationary. Okay, what is the flow of patents in the model? Here I'm just following Kortum. Remember we said the probability that a new idea exceeds the frontier is just 1 over k, this record-breaking temperature kind of result. So Kortum said, look, the fraction of ideas that exceed the frontier is going to be 1 over k. We're adding dk dt recipes, or ideas every instant. And so the flow of patents is just p of k times k dot, which is k dot over k. So the flow of patents in Kortum's model, or in my combinatorial model, is the growth rate of k. And in Kortum's paper, the growth rate of k was a constant. So he has a constant number of new ideas that exceed the frontier. And so that's the prediction of the Pareto model. It turns out the combinatorial growth model leads to much faster growth in the flow of new patents, right? To see that, suppose the number of ingredients rises with the number of researchers, okay? So each researcher adds 1 ingredient to the cookbook every year. And you can generalize that in interesting ways. That's done in the paper. Well, the growth rate of k, remember, is going to be the log of 2 times the change in n. The change in n, I just said, is proportional to the number of researchers. So the growth rate of K in the combinatorial model itself rises exponentially. Another way to say it, the number of new patents that exceed the previous frontier rises with the number of researchers, or the number of new patents per researcher would be constant. Now, if you make phi bigger or smaller than 0 up here, you can get that to rise or fall. But interestingly, the number of new patents should grow exponentially in the combinatorial model, and it should be constant in the Pareto model. And it's for an interesting reason. In the Pareto model, the distribution is so thick, the tail is so thick, that all you need is 10 ideas exceeding the frontier to get exponential growth in the max. In contrast, in the combinatorial model, new ideas are really small, right? Think about you're drawing from a normal distribution and you need a standard normal, and you need to exceed the number 10, right? It's incredibly hard to do it. That's why you need combinatorial growth in the number of draws. But even conditional on getting something that's above 10, it's probably 10.0001. If you want 2% growth in the max, you need a lot of ideas to exceed the frontier. In fact, if ideas are small, you need the number of ideas exceeding the previous frontier to grow exponentially. Okay, and that's a nice, difference in prediction. Kortum says the number of new ideas exceeding the frontier, the number of new patents should be stationary or constant. The combinatorial model says ideas are so small, the number of new ideas should be rising exponentially. What does it look like when we look at the patent data? Well, this looks a lot more like exponential growth rather than a constant. Now, Kortum was writing in the early 90s when the green line sort of looked constant, but post 1990, it doesn't look constant. Look at the total, which is really, patents from Samsung and Toyota and Mercedes-Benz all contribute to US growth. So it's probably the total that matters. And that thing looks a lot more like exponential growth than like a constant. But anyway, that's how that's a testable prediction that really distinguishes these models. Are new ideas growing exponentially, or are they constant? Okay, finally, let me just conclude. This is the last slide. With what can you do with this setup? What are some implications for future research? So first of all, wherever Pareto distributions have been assumed in the literature, maybe you can use thin tails if you're willing to use the cookbook model. So models of technology diffusion, like Lucas and Moll, Pearl and Tinetti, the trade literature, Eaton and Kortum, etc., search, productivity, all of these places. Maybe you can use thinner tails. That might be interesting. There's another thing that's worth noting, though. A beautiful feature of Kortum 97 is this Pareto assumption delivered 3 key results, right? It gives you a theory of growth, but it also gives you a Pareto distribution for markups and a Pareto distribution for the cross-section of firm productivity, a theory of firm heterogeneity. From one assumption, we get 3 things: growth, markups, and heterogeneity, and that's great. It turns out if ideas are small, if ideas are drawn from a thin tail distribution, you lose these connections. Combinatorics gives you the theory of growth. That's what I've shown you in this presentation. But it turns out markups and heterogeneity disappear asymptotically, right? And the problem is, if ideas are small, then the gaps between ideas are very small, and they're too small to give you a theory of proportional markups or proportional heterogeneity. So this is discussed at the end of the paper in more detail, but the way I see this is an opportunity. Maybe the combinatorial theory is right. The evidence on patents and ideas, I think, suggests maybe thin tails is the right way to think about it. But what that means is we've relied on Kortum 97 too heavily to give us a theory of markup heterogeneity and firm productivity heterogeneity. Maybe we need a new theory. The combinatorics and ideas won't give it to you, so we need a new theory of markups and heterogeneity, and I hope people are going to work on that in the future. Okay, well, thanks very much. Hope you've enjoyed the presentation.